Hi, in this video I'm going to talk to you a little bit about using the RMS package, which is a really nice package for doing a lot of reporting and even some model building features that are really good beyond what is ordinarily available in just regular R packages. So let's begin with, first of all, needing the RMS package. It's available as an R package like ALR4 or other kinds of packages. It's also good to also install the H miscellaneous package. It's capital H little m I-S-C, and that's a really good package also. In order to use the RMS package, you need to do a couple of kind of obscure statements like we did here with this data dist statement, and it is a command that operates on the Old Faith data set to make a new kind of packaged data object. And so you use the data dist command to make this object ddist, and then you have to declare ddist as a data dist kind of object, and that will facilitate a lot of the tools that the RMS package needs. So whatever the existing data frame is, in this case it's Old Faith, you'll need to execute two sort of similar commands like this, the data dist command and the specifying options. Once you've done that, you can create a simple linear regression model using the OLS command, ordinary least squares, and it will do the ordinary least squares simple linear regression model just like you've been seeing previously. There are some different options for this package, and you'll see the summary option. If you provide a summary of this model object, you get a very different looking kind of set of output than you do from the summary command from a regular LM model object in R. First of all, let's break it apart into its parts. The low column is the 130 seconds of duration, and you're comparing the waiting time at 130 seconds with the change going up to 267 3/4 seconds. This is the amount of change in the x variable that we're going to consider. Now, why was it 130 seconds and 267 seconds? Well, this would have been the 25th percentile, and 267 would have been the 75th percentile. Without any information completely specifying the change in x, or the change in the predictor variable we want to study, the default is the interquartile range from the 25th to the 75th percentile. That's a difference of 137 3/4 seconds. The amount of change in the waiting time is 24.36 minutes. The standard error is almost 3/4 of a minute. And then here is the lower confidence bound and the upper confidence bound for the underlying change in y. And so this is the default command for summarizing a simple linear regression model. The ANOVA command gives a partitioning of the variation with an ANOVA table like you're used to seeing in the rest of our notes. And then overhead 42, this particular overhead shows you some different summary commands, and these are nicely formatted for my PDF overheads, but you can see that underneath this is just the same summary command as I had on the previous page. It gives the same information about the lower boundary and the upper boundary for changing x. Now the next command is a little bit different because I've specified the lower and the upper boundary explicitly, 150 seconds up to 160 seconds. Well, that's a change in x of 10 seconds, and then you can see that the difference, and so that that shows you that the difference in the response is 1.76 waiting time minutes. The standard error is 0.05 minutes, and the lower and upper confidence boundaries for that particular change in y are given here. If I want just a 1 second increase like you see in regular simple linear regression output, it's this third command right here. For example, if I want to go from 150 to 151 eruption seconds, that's a change of 1 second, and you can see that change is right here. Here is the estimated slope for the summary least squares regression line, and the standard error for the beta hat is right here, and the lower and upper confidence bounds are given here. And so this would be just like what you would observe for LM function output from regular R analysis. On this plot, we are showing a shaded set of boundaries for upper and lower prediction intervals. So in this particular case, I'm showing the eruption duration from 120 seconds up to 200 seconds of duration, and the dark line in the middle is the estimated mean function. But the shaded set of boundaries is for a 95% prediction interval. And you can know that it is a prediction interval because I'm doing confidence interval type individual. And so this is for an individual eruption's waiting time. If you wanted to see what the shading confidence interval would be for just the estimated mean function, it is confidence type mean, which is on the next slide, overhead 45 out of 45. And you can see how much narrower the uncertainty interval or the confidence interval is when you're studying the mean function. The mean function is very well estimated by these data. However, the prediction for an individual eruption is quite variable. And the reason that is because individual eruptions are evidently quite variable. So even though we can estimate the mean function very precisely, individual values of y are quite uncertain as given by this prediction interval confidence type individual. Let me know if you have questions about that.